Get to the next page. All right, so this is why we worked on the summations. It's because we need to do what's called Riemann sums. There is a lot of notation here. I would like to simplify this for you, and I will try. But there are some problems in your homework where it actually references the more complicated notation, so I have to start with it at least. But you can simplify this as we start doing problems. So Riemann sum, you're going to see this now, and you're going to see this calc 2, you're going to see this calc 3. This is huge. This is what integration is really all about. We will now formalize what we discussed in section 5.1 for finding the area under a curve by rectangular approximation. So in 5.1 we found the area under a curve using rectangles, but we did only finite many rectangles. We're going to do more and more and more rectangles. Let f of x be a bounded function. So in other words, there's no asymptotes. It doesn't go to infinity. That's calculus 2. Have fun. So f is a bounded function on a closed interval from a to b. We subdivide, so we remember how we took our interval and we broke it up into 4 rectangles? Well, now we're going to subdivide it into n rectangles. So the formula is still the same. For the width of each rectangle, you just take b minus a and divide by n being the number of rectangles, b minus a being the length of your interval. Now, once you have this, you start at A and you add delta x, add delta x, add delta x to get all of your endpoints, just like we did before. So remember we drew a number line? So you start at A and you go to B. And you break this up into n subintervals. So the first one is going to be x0, that's your A, and then x1, x2, and in between each of these is a distance of delta x. That's why you got to find the delta x. Delta x is what gives you all of these values. We call this a partition. Our partitions will always have equal width in between. In this picture, you can see the rectangles don't have equal width. We're not going to do that case. I put this picture here though because I wanted to show you a picture with lots of rectangles. Just understand that our rectangles will always be the same base, same width. There are 3 techniques we will consider when constructing our rectangles: left-hand endpoint, right-hand endpoint, and the midpoint. Alright, so we're going to pick up where we left off. So I'm going to finish off 5.2 and then we're going to go to 5.3, which actually works out really nicely because the two are very strongly connected. So Riemann sums, let me start over. So a Riemann sum is basically what we were doing when we did the finite number of rectangles, but we're going to do more rectangles now. We're going to do it in terms of n rectangles. So we're not going to have a fixed number of rectangles anymore. We're going to do it for a general n. The reason for this is eventually what we really want to do is have as many rectangles as possible. Well, to have as many rectangles as possible, you just let n approach infinity. That should sound familiar because that's a limit. So we're going to take the limit and we're going to let n go to infinity, meaning we're going to have infinitely many rectangles. The more rectangles you have, the less you have extra area and the less you have missing area. Because the rectangles become so thin that they fit perfectly almost in the curve. And the thinner you make them, the more perfect they become. So if you can let those go to pretty much no width at all, meaning you have infinitely many rectangles, then you end up with a beautiful picture where you have basically the rectangles perfectly cover up the area under the curve. So what we talked about last time, when I stopped, was we're going to have an interval from A to B, so from A to B, and then we're going to partition that interval into n equal width rectangles. This picture doesn't have equal width, but our rectangles will be equal width because it simplifies a lot. So you're going to create your width by calculating it. Your interval, b minus a, divided by how many rectangles you want. In our case, we're going to do n. We're not going to plug a number in anymore. We're going to leave it as n. So we're going to have a number divided by n, and that's going to be the width of all of our rectangles, which creates these subintervals. So x0 is a, so then you add your delta x to get x1, add delta x to get x2, add delta x to get, and so on, all the way down to b, and that's called a partition. Once you have your partition, you then have to choose which method you want to use. So I've showed you left hand, right hand, and midpoint for calculating the area under the curve. So let's just consider one subinterval. So for one base of a rectangle, it goes from one x value to the next x value. So just think of it as like x1 to x2, x2 to x3. That's what this is representing here, just in general. So pick one base of a rectangle. Your choices are to use the value at the left side of your interval to find the height of your rectangle, meaning you take this x, you plug it into your function, and then that's going to be the height. Or you can use the right-hand endpoint, plug that into the function to get your height. Or you can find the midpoint halfway between. And that's what these three options show. Whichever one you end up, let's just call it CK. Okay, so that's the midpoint for the kth rectangle. So maybe we're somewhere over here, we're at this rectangle here, so we're finding the height of this rectangle. We can use the midpoint, we can use the left-hand side, or we can use the right-hand side to define it. Which, this picture here, it looks like they're using the midpoint because every curve, or every rectangle hits the curve exactly in the middle. So they're using the midpoint in this picture. So we pick our height based on these three. We plug it into the function to actually get the height value. The base is going to be delta x. The height is f of ck, just like before. So the area of one rectangle is the base times the height. And then we add all of those up. So we get n of these because we have n rectangles. So we have n base times heights. We add all of them up, and that's going to be called Sn. Now, something interesting to note, these rectangles can be negative in their height. So for example, if I were to plug in this midpoint here, my height would actually be the function value down here. Well, this is a negative function value, so the height is negative. When you have a negative height, your area is going to be negative. Interesting. So that means when we find the area here, the area that we'd be finding is this negative area and this positive area. So when you put the two together, they end up canceling each other out for a lot of it because there's almost the same amount of negative as there is positive. I think there's more positive, but pretty close. So this formula here is what we call the Riemann sum for a function f on an interval from a to b. So when I say Riemann sum, this is what I'm talking about. Base of the rectangle times the height of the rectangle and add them all up, but in general for n. So let me show you an example. Find the formula for the Riemann sum obtained by dividing this interval into n equal subintervals and using the right-hand endpoint for each. So they're telling us which endpoint to use. They want us to use the right-hand endpoint. Check your work, or check your homework, it might tell you. But you're going to see in a few minutes that it really doesn't matter. And I'll explain that later. All right, then take the limit as n goes to infinity to calculate the area under the curve f of x equals 4 minus x squared over the interval from 0 to 2. All right, so a couple things that we're going to need. First of all, delta x. What was the formula for delta x? If you don't remember, go scroll up and look, or go look in your notes. B minus a over n. Again, we're leaving it as a general n. So we have a and b are our interval values here. So 2 minus 0 divided by n is 2 over n. So then we need to have our number to plug in to our function. So we need our right-hand endpoint. So if you think about the interval, we go from 0 to 2. So our first interval is from 0 to 2 over n. That's the first interval because that's the width of our interval. We add 2 over again, we get 4 over n. And then we get 6 over n. And then we keep on going and going and going until we eventually end up with 2. If we add enough of these together, we end up with 2. Now, how are we going to make this easy though? Because we can't just go and plug all of these numbers into the function. We got to create a formula. So what we're going to do is we're going to take our endpoint a. So ck is going to start at a. Now we want the right-hand endpoint. So our first value we want is to be a plus 2 over n. So our a value plus 2 over n, because for our first interval, we want to end up with this number here. So when for C1, the right-hand endpoint for the first interval, subinterval, when we plug into our formula, we want the answer to be 2 over n. When we plug in 2 for our formula, we want the answer to be 4 over n. When we plug 3 into our formula, we want 6 over n. And when we plug in, if we keep on going here, n into our formula, we want the answer to be the 2. The right-hand endpoint, the last one would be the 2. All right, so how do we create this formula? So that's the CK. We got to make this. So in general, it's going to be a plus your delta x times your k. So in our case, a is 0. That's the first value in our interval. Plus our delta x, that's the 2 over n, times our k. Or you can write 2k over n. So the 0 is gone, so it turns out for us that ck is 2k over n. Now, whether you do left hand, right hand, or midpoint, it really doesn't matter in these problems unless they ask you for an earlier formula. So this is for the right hand. Just in case the problems ask you for a first step answer or ask you for, I don't know how, if they ask you for anything before you take the limit, it's going to be a little bit different. So let me go ahead and show you how we would do a left hand. So left hand, ck would start with 0. We want to have the first term be the 0, the left-handed point. And then c2, we want to be 2 over n. So it's going to be the same numbers, we're just going to start at a different value. So how are we going to adjust? Well, it's going to end up being a plus delta x times k minus 1. So for our case, a is 0, delta x is 2 over n times k minus 1. Or just 2 times k minus 1 over n. So this is the general form for the left hand. So if you need that, there it is. Let's just check it. So if k is 1, we get 1 minus 1 is 0. So the whole thing is 0. If k is 2, 2 minus 1 is 1. So we get 2 over n, And then the next one would be 4 over n and 6 over n. And it works. I don't think you have any midpoint ones in your homework. See, is there an easy way for me to explain the midpoint ones? For the midpoint ones, let's see, it would actually be one of these formulas just slightly changed. It would be, if I divide by, I wonder, I don't have my notes. Honestly, I don't think you have any midpoint. I think they all are left hand and right hand. If I'm wrong, then I'll do another video, because the midpoint really is kind of weird. All right, so those are just the general formulas. Let me circle them so you have them highlighted. So here's the general formula for the right hand, and here's the general formula for the left hand. So that should help you. All right, so once you have all that, we're going to do the right hand one. So this is going to be our formula that we're going to use today. You then need to find f of your ck. So our f function was 4 minus x squared. So 4 minus our x squared. X, though, is what our ck is. So 2k over n. And if we work that out, we get 4 minus, we square the whole thing. So everybody gets squared here. So 2 squared is 4, k squared over n squared. Then the Riemann sum says we need to take our height that we just found, multiply by delta x, and then add them up. So Sn is equal to the sum as k goes from 1 to n. This is our f of ck. So we plug that in for our height of our rectangles. Times the delta x, which is the base of our rectangles. What was our delta x? 2 over n. And that we need to simplify a little bit. So let's see. How can we simplify this? Well, what's the easiest way to approach this? See, I'm looking at this and saying, okay, we're going to be working with summations here. And we did summations in the last video. We want to simplify the summation. Honestly, we want to get rid of the summation using our formulas for finding the sum of summations. But do I want to distribute the 2 over n, or notice k is what's changing here. This is a constant. We could pull him all the way out. It's really up to you which way you want to do it. I'm going to distribute him and pull him out of the individual summations. I think that would be easier. So let's distribute that into the parentheses, the 2 over n. So 2 over n times 4 would be 8 over n, minus 4 times 2 is 8k squared over n cubed. And now, like we did before, this is the summation of a subtraction. So what we could do is do each one separately. I'm just going to keep working down here. So k goes from 1 to n of 8 over n. And then we're going to do a separate summation, minus the summation as k goes from 1 to n of 8k squared over n cubed. Now, k is the variable, so k is what's going to stay inside the sum. Everything else can come out. Well, that means this is a constant. If this is a constant, we already know the formula for that sum. If this is just a constant here, the sum of a constant, so this number added over and over and over again, n times, you just take your constant times the number of times you're adding it. So this is the C times N formula. Constant times the number of times you're adding it. Minus, over here, now this one we gotta do some work. 8 is a constant, and N cubed is a constant. So that can come out, and we end up with the summation of what's left. Just the K squared, as K goes from 1 to N. This guy here, we have a formula for. This was the big formula. And I don't want to get it wrong, so I am going to pull up our lecture notes to make sure I get it right. Let's see. Where are they? Lecture notes. Almost there. There we go. All right, the sum of K squared. All right, yeah, I didn't want to get this wrong. You do need to have this memorized, by the way. N plus 1, 2n plus 1, all over 6. So this is going to be n plus 1, 2n plus 1, all over 6. And that's just the box. We still got to bring everybody else down in front. So we still have the minus 8 over n cubed multiplying by that sum. Also over here, we can actually simplify. The n's cancel, and we have left here an 8. Keep on working down here. All right, so let's see, what can we do? Well, we can reduce one n from the top and one n from the bottom here. We can reduce the 8 and the 6 each by 2, so that leaves us with 4 and 3. So 8 minus 4. I'm going to FOIL these parentheses together. So n times 2n is 2n squared. N and then 2n make 3n. And then 1 times 1 is 1. And don't forget this is over 3 and n squared. Alright, so we have, let's distribute that 4. 8 minus 8n squared plus 12n plus 4 all over 3n squared. Actually, all right, I think we're good there. So remember, we found the Riemann sum. This is the Riemann sum. Now we have to let n go to infinity. So if this is our Sn, to find S infinity, I'm going to go up here so my notes don't get too big. So S infinity is going to be the limit as n goes to infinity of this mess. Now, why did I say, well, that's good enough? Because that is something we can take the limit of. We have 8 minus 8n squared plus 12n plus 4 over 3n squared. The 8 is a constant, so he just chills out. He's going to stay. Minus, limit of a constant is a constant, remember that? This guy here, this is a rational expression with the power on the top and the bottom are equal, so the limit is just the coefficients in front. That'd be the 8 over 3. So if we get a common denominator here, we end up with 24 over 3 minus 8 over 3, or 16 over 3. This would be the sum of infinitely many rectangles under this curve, which means this is the area under the curve. There you go. So yes, those can be a little bit challenging. They put a lot together, so you have to do, well, you have to do a lot. You have to find your endpoint that you're going to plug in. You have to plug it into your function. Then you have to create your Riemann sum, simplify the summation, get rid of the summation using the summation formulas. Then you have to take the limit, and you're going to need your limit rules. So yes, there is a lot in there, and